But then on this side, notice that this arrow is going here, and this arrow goes here, the two arrows collide. That's not one continuous curve going around. To have a continuous curve going around, the arrows must not collide. This side, the arrow comes in this way, continues this way, that's no collision. So it has to be the right one. Suppose I have this picture. Right one would be this way, left one would be this way. Which one is the correct now? Now, Colton says the left one is correct. Exactly. The arrows are going this way too, right? So the two arrows are in the same direction. In this direction here, the arrows will be colliding on the right one. So the one that has arrows not colliding is the left one. So for this one, the correct infinite semicircle radius is the left one. Okay? So, suppose that I had this plot, and suppose -1, 0 was here, and my system is open loop stable. Would this closed loop system be stable or not? No. I'm telling you it's open loop stable.
Oh, it is open.
Is this system closed loop stable or not? No. Draw this line. Which way does the infinite semicircle make us turn? Clockwise. So that's n equals 1. It's open loop stable. P is 0. 1 plus 0, 1. Closed loop unstable with 1 positive. Closed loop open. In this case,
Yes.
I can draw this. No cuts at all. N equals 0. But if I do this, I have counterclockwise cut here. This moves me up, so this is counterclockwise. But the infinite semicircle is clockwise. If I had drawn the semicircle the wrong way, I would have gotten n equals -1. Okay? Which, if it was open loop stable, would have told me I messed up, because I would have gotten z equals -1 plus 0 -1, and then that means I messed up. But if it was open loop unstable with one positive pole, I would have gotten the incorrect conclusion that it's stable, when in reality it's not.
So the left is unstable and right is stable?
No. If z is 0, it's stable. If z is positive, it's unstable. So, what I said here, in this case, if this was stable, open loop stable, if P was 0 and I had drawn the wrong infinite radius semicircle, this cut would have given me -1, right? So I would have had 0 plus -1, -1, and getting z equals -1 means I messed up. So that would be a hint, maybe I drew the wrong infinite semicircle. But what if I had P equals 1? If I had P equals 1, drawing the circle the wrong way would have given me n equals -1, and I would have gotten z equals 0, stable. While in reality, the circle is this way. In reality, the circle is this way. So n is 0, since P is 1, z is 1, and the reality would have been closed loop unstable. Okay, so let's do as an example, but let's also do it on the computer. Last year's exam, last problem. So if we go to posted exams, and I've posted a lot of exams, guys, so you get a lot of stuff out of this class. We can go, not last year, spring semesters, exam 3, spring 15. And by the way, exam 3, spring 15 could have been your exam because it starts. So I guess in spring I was also behind, because I did this problem in exam 3, not in exam 1. So start with the first order plus time delay problem, and then he has a Ziegler-Nichols tuning problem, and then let's go to problem 3. Now to problem D.
You can't see it.
No. Oh, oops. Sorry.
I can see
That's the one I'm looking at, right? Let's go to problem C, to problem 3. So this is spring 15, just previous semester, problem 3. So let's start with that. Go for it. It's time. Exam 3. Look, wait. Oh, I know. My bad. So I had on the computer, I had DVD VCR. You forgive me one that since I'm having technical problems from this screen, I'll go to the other screen.
That goes for us. What's the exam that we're looking at?
Spring 15, exam 3. Problem 3. So, consider a process with transfer function, this one controlled by that controller. Write a transfer function with Bode or Nyquist plot can be used for determining closed loop stability. So, what is the transfer function that it's GOL, right? Which is GU times GC. I think I can get this up. But for the moment, I'm not this. So, and you should expect the majority of the exam to be straightforward. I will have a 5 to 10 point problem that would require some thinking.
Oh,
We have 2 good candidates for that.
God damn it.
That will not be like any previous exam problem exactly. It will require you to understand it.
Goodbye.
But the majority of the exam is going to be very straightforward. All right. So I'm giving you GU equals -10 over -6 plus 4s. So I've written in the way we entered in the program. Plus 0.4 s squared e to the minus 0.1s. And I've given you the controller. So you should all know the controller transfer functions. What kind of controller is this?
Integral action. PI.
PI, right? It doesn't have integral action. It doesn't have derivative action. It's PI. So for a PI controller, and you have the parameters. What's KC? 2. And what is tau I?
Negative.
Or -2. That's important. That's very important this time. 10. Okay? Plus 1 over 10s. So you can rewrite it -2 times 10s plus 1 over 10s. So GOL, which is the product of the two, is numerator -10 times -2 times 10s plus 1 over -6 plus 4s plus 0.4 s squared times 10s. So let me multiply by 10.
Where does it say it's PI?
In your brain.
You have to know?
You need to know those things. You need to know the controller transfer functions, guys. So, denominator is that times 10s. So, -60s plus 40s squared plus 4s cubed. All that times e to the -0.1s. Or finally, multiply through, you have 20 times 1, 20 plus 200 times s over -60s plus 40s squared plus 4s cubed times e to the -0.1s. So that's the answer for full credit to part A.
You can simplify it if you want to.
Where?
Does that change it?
Alright, yeah, that's fine.
I can go up to 5.
Alright, determine how many poles with positive real part GU has. How do I do that? Truth array of what? So that's part A.
GU?
Part B, that's part A. Part B, I'm talking about open loop stability. The Nyquist will be for closed loop stability. But to do the Nyquist, I need to know how many positive poles GU has. So that's what I'm asking to determine here. So, for part B, denominator of GU here's my GU, -6 plus 4s plus 0.4 s squared. It's a quadratic, so you could solve for the roots of a quadratic, but it's faster to do root array. No Padé. If anybody did Padé here, they lost a lot of points. Okay, how many points does that have? Probably I gave them less than half. Okay, so they lost at least 5 points, if not 8, I'm not sure. So, also they complicate the exam. Because instead of having a quadratic, they changed it to a cubic. And then they messed up, okay. So I think if they did correct with the cubic, they got 5 out of 10. If they really messed up the cubic, then they got almost no points. Well, the quadratic is very simple. How many, since I have a quadratic, how many rows? 3. Start with the coefficient of highest power, 0.4. Skip the next coefficient, -6. Coefficient of the second power 4. And corner, -6.
So 1.
So, what do I have on the left column? Left column is plus, plus, minus. How many sign changes? So the system is open loop unstable with one positive pole for G. Make it okay? All right. So now let's go to the C part. I'm giving you both the N-Nyquist plots.
And you can't destroy that.
Assume that the body Nyquist plot for the transfer function you specified in part A are as shown below. I give you both the body and a Nyquist plot. Using the plot of your choice, determine here whether or not the closed loop system is stable. Obviously, if students chose body, they got 0 points. If they did both, they lost a lot of points.
Why?
Because the body doesn't give us any information. So the body turns out to also give stable. So it's irrelevant. Again, guys, get used to it. I'm grading on concept. So if you do both, you make a serious conceptual error.
But then you only lose like 10 points, right?
If you did both, you still get, probably I took 5 points off it.
Okay, okay.
I didn't take all the points off. But if you did only body, you got 0.
I'm not sure you still on
Okay? So, in this case, clearly we have to do Nyquist, but since here I want you to learn how to do it on the computer and I want to discuss some things, let's go back to our program. So, we want to enter that and do a Nyquist plot for the GOL we just wrote there. Okay, so for this GOL, we want to do the Nyquist. So, change transfer function. I need to dim the lights. I guess, right? Mika, do I need to dim the lights? Or can you read it fine?
Yeah. I know. Yeah, dim the light.
Dim the lights. So, what's the time delay I have? It's 0.1. What's the degree of the denominator?
3.
3. 0 for the term 0, right? I have no 0 for the term, 0. And that will always be the case when I have integral action, because s multiplies the denominator, so there will be no 0 for the term. Then the next one is 60, minus 60. The next one is plus 40. And the last one is plus 4. What's the degree of the numerator? 1, right? 20 plus 200 is. So 1. And the first one is 20. And the next one is 200. That's it. This is a case, guys, where you really want to check specific frequency values. Before, kind of, I want to show you. What did I use before? I used 0.001 as minimum frequency, right? And maximum frequency, I used 100, right? Okay, don't do what I'm doing now. Okay, just watch the screen. Let me click here to continue. And let me say no to specific frequency and put the values I put before. 0.001 and 100. And 1600. We can look at the body plot. It's actually the plot I printed.